Hi students, this is a second educational video among a series of other tutorials showing how to analyze a loaded frame in terms of normal force, shear force, and bending moment diagrams. Of course, I'll explain this as simply and as clearly as possible. Okay, let's go. Well, first let's describe our problem. So we have a simple frame A, B, C, D as it is depicted by this slide. This frame is constituted by a left hand and a right hand column as vertical elements and a beam as horizontal element. The height of the frame is h equal to 4 meters while its span is s equal to 6 meters. The frame is supported by a pivot support at the bottom of the left-hand column at the point A and a roller support at the bottom of the right-hand column at the point D. The frame is loaded by a uniformly distributed load UDL equal to 6 kN per meter along the beam and a point load PL equal to 7 kN applied at the half height of the left-hand column. The frame analysis consists in 5 steps. The first one is the checking of determinacy. The second one is the determination of the reactions at the point A, B, C, and D. And the third step is the drawing of the normal force diagram for columns and beam. The fourth step is the drawing of the shear force diagram for columns and beam. And the fifth step is the drawing of the bending moment diagram for columns and beam. Now for the determinacy checking, it's to note that our frame in this tutorial is supported by a pivot support and a roller support exactly in the same way that the frame analyzed in the tutorial number 1. So I invite you to see the educational video frame analysis tutorial 1 that I shared the link in the box description. Now I'll explain how to determine the external reactions applied on the considered frame. We have the uniformly distributed load UDL applied along the beam. This UDL can be simplified into a point load with a magnitude equal to the UDL multiplied by the span S and applied at the point G at the half span of the beam. If we consider the directions x and y as it is depicted by this slide, x is the horizontal direction and y is the vertical direction, we have a reaction RAX. This reaction is horizontal and applied at the point A, and another vertical reaction applied at the point A denoted by RAY. This is expected since at the point A we have a pivot support. At the point D we have a roller support, so we have a single reaction which is a vertical reaction denoted simply by RD. In order to avoid complications during the calculations of the reactions, we will apply the static equilibrium equations of moment at the point A. This will permit to neutralize RAX and RAY in order to directly find RD. If we apply this static equilibrium equation of moment, we will have finally a reaction RD equal to the half span multiplied by the UDL plus the half height multiplied by the point load and divided by the span, which will give numerically 20.33 kilonewton as RD. Now, in order to determine RAX, we will apply the static equilibrium equation of forces along X. When we apply this static equilibrium equation, we will find finally that RAX will be equal to minus the point load PL, which will give numerically RAX equal to minus 7 kilonewton. So the reaction RAX is in the opposite direction of X. Finally, in order to determine the reaction RAY, we will apply the static equilibrium equation of the forces along Y. And when we apply this, we will find finally that the reaction RAY will be equal to the UDL multiplied by the span minus the reaction RD, which will give numerically 15.67 kilonewton as RAY. Now I'll explain how to determine the normal force diagram based on the free body diagram. This free body diagram explodes the frame into columns and beam, and it shows the external forces applied on the columns and the beam. Notice that the left-hand column is subjected to a normal force applied at the bottom of the column with a magnitude equal to 15.67 kilonewton. In order to maintain the equilibrium of this left-hand column, we have to add another force applied at the top of the column and with a magnitude equal to 15.67 kilonewton as the same magnitude for the external forces applied at the bottom of the column. In the same way, we have to generate an internal forces equal to 20.33 kilonewton applied at the top of the right-hand column in order to neutralize the external forces applied at the bottom of the right-hand column and maintain equilibrium of this column. Now, the 15.67 kilonewton applied at the top of the column will be transferred to the left-hand edge of the beam as shear force. At the right-hand edge of the beam, we have the forces equal to 15.67 kilonewton as the shear force applied at the left hand of the beam minus the UDL 6 kilonewton per meter multiplied by the span 6 meters, which will give finally minus 20.33 kilonewton, which is 20.33 kilonewton but applied in the opposite direction of Y. Now, based on this free body diagram with the applied external and internal forces, we can determine the normal force diagram. Note that for the left-hand column, we have a normal force equal to 15.67 kilonewton. It's a compression force, so we will have minus 50.67 kilonewton applied along the left-hand column. For the right-hand column, we have a normal force, a compression equal to 20.33 kilonewton. It's a compression, so we have a normal force equal to minus 20.33 kilonewton applied along the right-hand column. For the beam, we have only shear force. We have not normal forces, so we will have 0 kilonewton as normal forces along the beam. Now I'll explain how to determine the shear force diagram. So always based on the free body diagram with the applied external and internal forces, we can deduce the shear force diagram. For the left-hand column, notice that we have 7 kilonewton applied as shear force at the bottom of the column. So we will place this on the shear force diagram. Since it's a shear force, this 7 kilonewton. And notice that we have at the half height another 7 kilonewton in the opposite direction, which will neutralize the 7 kilonewton as shear force applied at the bottom of the column. So for the lower half height of the left hand column, we have a shear force equal to 7 kilonewtons on the opposite direction of X, so it will be minus 7 kilonewton. And for the upper half height of the left hand column, we will have 0 kilonewton. Since as I explained, this 7 kilonewton will be neutralized by another 7 kilonewton, the point load applied at the half height. For the right hand column, notice that we have only normal forces, we have no shear forces, so the shear force will be 0 kilonewton along the right hand column. Now for the beam, we have a shear force equal to 15.67 kilonewton applied in the left hand edge of the beam. This shear force will be placed in the left hand edge of the beam in the shear force diagram. And we have also shear force equal to minus 20.33 kilonewton applied at the right hand edge of the beam, which will be placed, uh, of course, at the right hand edge of the beam. Since the variation of the shear force along the longitudinal direction of the beam is equal to minus the applied force here is the uniformly distributed load equal to 6 kilonewton per meter. This UDL will be the slope of the variation of the shear force along the beam. Now we can determine where at the beam the shear force is zero using the simple equation of the line indicating the variation of the shear force along the beam. We find finally that the shear force will be zero at the distance x equal to 2.61 meters on, of course, on the considered beam. Now I explain how to determine the bending moment diagram. This bending moment diagram is determined based on the shear force diagram, since the variation of the bending moment along the longitudinal direction of the column or of the beam is equal to the shear force. So the bending moment is the integral of the shear force. Now notice that the shear force applied on the left-hand column is equal to a constant minus 7 kilonewton applied over the lower half height of the left-hand column and the 0 kilonewton applied over the upper half height of the left-hand column. Since the bending moment is the integrate of the shear force, it can be determined as the area of the evolution of the shear force, and it will be like it is depicted in this slide. It varies from 0 kilonewton meter at the bottom of the left hand column to minus 14 kilonewton meter at the half height, and it will continue to be minus 40 kilonewton meter over the upper half height of the left hand column, since we have no shear force at or over the half height of the column. For the right hand column, notice that we have a 0 kilonewton, so the bending moment will be constant or 0 kilonewton meter. Since we know that the bending moment at the bottom of the right hand column is equal to 0 kilonewton meter, since we have a roller support, so we can deduce that the bending moment will be 0 kilonewton meter over the right hand column of the frame. Now this minus 14 kilonewton meter applied at the top of the left hand column will be transferred to the left hand edge of the beam as plus 14 kilonewton meter, and this 0 kilonewton meter applied over the right hand column will be transferred to the right hand edge of the beam. And as I said, since the bending moment is the integrate of the shear force, the maximum bending moment can be determined based on the area 2 of the shear force variation, and it will give finally 34.45 kilonewton meter applied at the distance x equal to 2.61 meter, which is the distance where or the point where the shear force is zero. When the shear force is zero, the bending moment is maximum. Of course, since the variation of the bending moment along the longitudinal direction of the beam is equal to the shear force. And this maximum bending moment, 34.45 kilonewton meter, is obtained as 14 kilonewton meter, which is the bending moment applied at the left-hand edge of the beam, plus area 2. And we can determine finally the evolution of bending moment diagram, always taking into account that the bending moment is the integrate of the shear force. It's to note also that we can verify the bending moment equal to 0 kilonewton meter applied at the right hand edge of the beam based on this area 3. So the bending moment applied at the right hand edge of the beam, which is x equal to 6 meters, would be equal to the maximum bending moment, 34.45 kilonewton meter, minus this area 3, which will give finally 0 kilonewton meter. This educational video takes end. Please, if you have any remarks or suggestions, please don't hesitate to mention it in the comments. Thank you very much for your attention.